In this recording, we will be continuing working on the same example that we started with, which is about, about houses and predicting the price of houses given some predictor variables. In the first step, what we did, we built the linear model, including all of the predictor variables. After that, we said, okay, let's do, and we did many things. We did the interpretation of the coefficients, then we estimated the prices for some given values, and we constructed confidence intervals and prediction intervals for some given values. Also, next step, we did model selection. In the model selection, we found what is the joint significance of these variables and the individual significance of these variables. We found that one of the variables is not significant, which is the beds. So we excluded the beds from the model. We built another model that doesn't include the beds, right? And we built other models as well, just in general, to check which model we're going to pick. And based on the measures that we selected, based on the good of fit measures, we said we are going to look at the highest adjusted R-squared or the lowest standard error. We found that the second model was the best one, or model number one was best one, the one that doesn't contain beds, right? So this is going to be our model now. This is the model that we're going to use to test for the assumptions. And conducting assumptions on linear regression is crucial. It's a crucial step in the modeling process. Why? It ensures validity and the reliability and also the interpretability of the results. So that's why we have to conduct assumptions tests, okay? Because violations of the assumptions may lead to biased estimates and incorrect conclusion. The violation may compromise the accuracy. The violation maybe is going to lead to a problem with the relationships between the variables, right? And misinterpretation of the results. So that's why we need to conduct the assumptions. Number one, the first assumption, we have to determine whether the model is linear in its parameters or no. To do this, we're going to create plots. If you remember, it's all about plots. So it's going to be easy. This class is going to be easy. So we're going to create plots. So we are going to use a function called plot. This rich function contains so many arguments, but we're going to use now very few arguments. Okay. So we're going to create residual plots to identify the nonlinearity, and we are going to use what? The residual plot versus the fitted values, or the residual versus the predictor variables. The problem that you will not be able to use if you have categorical variables is not logical, reasonable to use the residual versus categorical variable. Like in our binary variable, which is colonial, we have 0s 1 only. So when you graph it, it doesn't make sense. It's not going to give you exactly what's happening. So that's why I prefer personally to use the residual versus fitted. So we're going to do like kind of light assumptions check, okay? And this is going to be helpful. So we're going to create residual plots to identify nonlinear patterns. Okay, we can do residual versus fitted or residual versus predictor variables. In this case, we're going to use the function plot. Plot what? Plot what? Do you remember which model we picked? Is L model 1. This is our model. Let me go back. This is L model 1. This is it. Let me copy it. Just to pick it, just to put it here, just to see it. This is the one that we already selected. If you run it, we ran this already. Let me run this. If you run the plot, you're going to get four different charts. Okay, so we need the residual versus the fit, which is the first one. So number one. So if you'd like just to see the first one, you can add argument called which. So comma which equals 1. Run this. You're gonna see only the first one. Okay, you're gonna see only the first one. If you don't want to write which, you're gonna see all of them. What do we expect here? We expect to get non-linear pattern. Non-linear pattern. Do we have non-linear pattern? Do we have a random? Yes, we have a random stuff here. Random, scattered. So we are good. So we have a really good residual versus fitted values. What are the fitted values, by the way? They are the estimated price. These are the estimated price values. And these are the residuals, the error, the difference between the observed and the estimated price. So what we are expecting to have a random or scattered around the just scattered everywhere. It's not that we do not have a pattern. We don't have like a funnel pattern. We don't have increasing, decreasing pattern. We don't have a non-linear pattern. So what we conclude that the linear regression analysis, by conducting this, the linearity assumption was assessed, and we found that it's met. Okay, and the relationship between the price, square foot, baths, colonial can be captured by a linear model. So this is exactly what we are going to write down. So the linearity assumption is assessed and found to be met, right? This indicates that the relationship between the price, square foot, baths, and colonial style is captured by the linear model. So good stuff. We have a good stuff for the first one. The second one, the second assumption, we are assuming that there is no exact linear relationship among the predictor variables. So there is no perfect collinearity. There is no perfect collinearity. We are going just to do one thing here, basically. I'm not going to put so many tests. So it's just enough to find the correlation between the predictor variables, okay? High correlation, okay, it's gonna be a sign for multicollinearity. How much high? High is going to be between above 0.8 and less than negative 0.8. In this case, we are going to consider that we have a multicollinearity issue. We have a relationship between two variables. That means we have an issue, okay? So this is the test that we're going to do, just the correlation. How to find the correlation? There's a function called COR, correlation, COR. And the correlation, I'm going to go to my data. Do you remember my data? It's my data set. I'm going to study the correlation between all of the variables and see what's going to happen. We are lucky if you look at the structure, if you go back to the structure of my data, all of them are numeric, right? So let's study the correlation here. So there is no need to have the price. The price is the response. The goal is to study the correlation among the predictor variables, and the price is not a predictor, it's the response. So I'm going to take it off, okay? Brackets, if you remember, I'm going to have all of the observation. I'm going to just subtract the first column, take it off. -1. Take off the first column. Run this again. We removed that one. If you notice that the diagonal, the main diagonal is 1, because square foot with a square foot by itself, we have a full correlation, complete perfect correlation. It's 100% 1, and like bids 100% or 1, and this is 1. This is 1, right? Also, we would like to take off the bids, because bids is not part of our what do you call it? Of our model, right? This is, I mean, if you look at my data, this is the first column, second, third column. So we're going to exclude the third column as well. So now we are good. If you look at the correlation now, square foot with baths, we have kind of a high correlation. It's not very high, but we have to look at this carefully. It's not above 0.8. It's not above 0.8 or less than negative 0.8. By the way, the correlation coefficient, if you forget, it's between -1 and 1, okay? So highly positive correlation means above, let's say, above 0.8. Highly negative correlation is less than negative 0.8. In this case, we don't have above 0.8. It's a moderate correlation, but we have to look at this carefully. We have to watch it only. 0.5 is okay between the colonial baths. 0.3 is low, so that's good. In general, we have a good let's say good, or we have almost met the second condition. So we do not suspect of any, or let's say there is an absence of a multicollinearity among the predictor. Okay, kind of multicollinearity. Okay, absence. Okay, this is the second assumption. So the third assumption is going to be what? It's going to be, we need to look at the variation of the error term. It has to be constant. We said it should be an absence of the heteroscedasticity condition, right? And we are going to use a plot called a scale location plot, which is a spread location plot. And this plot is used to assess this assumption, and that tells you the variance of the residuals should be constant across all levels of the predictor variables. Okay, and how to create this? So we're going to use scale location plot. In the scale location plot, the x-axis. Okay, how first? Let me just show it to you. the plot, it's in our model. Do you remember the four charts? It's one of them. It's the third one. Which 3? So this is equal. What's the problem here? Okay, let's delete this. Model 1. I don't know what's the problem. Maybe which is wrong. Here we go. Maybe misspelled it. So this is a scale. The scale, let me take this up a little bit down. Okay. So the x-axis typically represent the fitted values or the predicted values. And these are from the regression model. The y-axis represent, look at what, is the square root of the standardized residuals, or sometimes they use the residuals absolute value only. So what we are looking for this, I mean, when you look at the scale location fit, the scale location chart or plot, what we are looking at, technically we want to see horizontal line with roughly constant spread of point across the range of fitted values. If we have seen this, then this suggests the variance of the residual is approximately constant. If there is no clear patterns or trends, then we are good. If you observe like a funnel shape or systematic pattern, this may indicate having a heteroscedasticity issue. Why? That means the spread of the residuals systematically changes with the predicted variables. And what can you tell me here? In this plot, it seems that it follows a pattern because it's kind of between two parallel lines, but these two parallel lines are increasing. They are not horizontal lines. So it suggests the presence of heteroscedasticity here. We don't have like, look at the errors, they are kind of increasing. They are not constant, right? Because the variance of the residual is not constant across all of the across all of the fitted values, right? We have an increasing case here. So in this case, so we have an issue. So we have an issue of scedasticity. There is an issue of heteroscedasticity, right? That's spelling. So you have an issue with the variance. You have an issue with the variance. So let's move to the next assumption, right? To the next assumption. But before we move to the next assumption, having a heteroscedasticity, this may affect the reliability of our t-test and f-tests. Maybe we may not rely on the standard errors. It becomes more inappropriate. But again, this is not like, it's not a holy stuff. It's not something that, but we need to consider this. We need to keep this in our, we look at the whole picture, not only one picture, okay? Assumption 4, the error term epsilon is uncorrelated across the observations. So in this case, we are going to look at either a residual versus fitted curve or plot, or we look at the residuals versus the time order, and this one is not available here. Or sometimes we are going to use something called Durbin-Watson DW test. So the idea is the error time is uncorrelated across the observations. That means we are assuming that there is no autocorrelation. There is no autocorrelation. So in this case, I'm going to use a test called DW Durbin-Watson test. What does this test tell you? Use autocorrelation test. DW Durbin-Watson. What is the hypothesis testing here? We used each note for this test. Rho, which is the autocorrelation, is 0. What does this mean? That there is no autocorrelation. What does it mean we don't have an autocorrelation? So the error term is uncorrelated, i.e. the error term is uncorrelated across observation. Okay, observer. What about the alternative hypothesis, which is HA? Rho is not 0. Rho is not equal to 0. Okay. But to conduct this test, we need to call a library called CAR. So you have to install this package first, okay? So I'm going to call it because I have it. First, you have to install it, CAR. The test called Durbin-Watson test. No, not this one, the other one. And model 1. So we got values. So Durbin-Watson statistics is, it's less than 2. This number is less than 2. But the p-value is not significant, okay? Is not significant. But before we talk about these values, let's first say what do we expect from the Durbin-Watson test. Okay, the test for the autocorrelation in the residuals, and the test values ranges between 0 and 4. So this number ranges between 0 and 4. The values about the two says that there is no correlation. There is no autocorrelation. There is no autocorrelation. So we are looking for the values about to be 2. If the values, again, we have to look at the significance of this. Do we need to adopt this one or no? Do we need to, like, is it significant or no? Okay. So if this is not 2, if this is not, like, if it's 1 or 4, you cannot say that, oh, we have an autocorrelation, so that means the residuals are correlated. No, you have to look at the p-value. The p-value has to be significant. So what is the significance level we're using? Typically is 0.05. If this is less than 0.05, then we say we reject the null hypothesis. So we reject this. But this is not less than 0.05. So we fail to reject this fact. We fail to reject this. Right? So yeah, it is 1.6. It's less than 2, but the p-value is not significant. As I said, if the p-value is greater than the significance level, we do not have enough evidence to reject the null hypothesis. So based on the given p-value now, there is no enough evidence to conclude that there is autocorrelation in the residual. So we have no problem with this. We do not have an autocorrelation problem. So there is no sense p-value is less than 0.0. No, it's not less than. Is not less than 0.224, sorry, 0.05, then we fail to reject the null hypothesis. So there is no evidence of having an autocorrelation issue. Autocorrelation. Okay, so we don't have any violation for this assumption. This test is good. We can use it. Again, as I said, we're gonna do only light tests, okay? Light tests. For the assumption 6, we need to look at the error term with their 5 assumptions. We have 6, right? But we skipped the 5th one. We will not talk about the 5th one. Just we will test the 5, which is enough. The error term, the epsilon, has to be normally distributed. And we look at, just watch QQ plot. And all of the plots, by the way, they exist on the same model. We can't see them, right? What do we expect? So the points of the QQ plot, they have to form. Let me just show it to you. Plot L model 1. And basically, let's look at which one. This is a QQ residuals, which 2 equal to. Yeah, what do we expect to have a normally distributed residuals? We expect the points to be on the straight line. And they are almost on the straight line. They're almost on the straight line. Oh, we have some outliers. That's okay. Just 1 or 2 outliers. That's fine. Most of the residuals, QQ residuals, are on the straight line, so we can say that the residual follow a normal distribution. Okay. We can, by the way, use another test called Shapiro, or you can, and to confirm, let's use Shapiro-Wilk test. Yes. What does it say, Shapiro? Shapiro, we have null hypothesis of the Shapiro. Not hashtags, it's $sign, because mathematical, I'm typing math here. Shapiro, the null hypothesis, the H note is going to say what? Data follows normal distribution. Okay, this one, data does not follow normal distribution. So data here, in this case, means residuals, okay? So this is the test for normality, and let's conduct that one, by the way. So we're gonna use this and see what's gonna happen. It's called Shapiro test. It's in L model 1, but I'm going to pick the residuals because we are studying the residuals. So I'm going to take the residuals from the L model 1. Okay, we're going to see the distribution of the residuals. Okay, what we got? The value we got is 0.97, right? But the p-value is not significant again. The p-value is not significant. If the v-value is less than 0.05, the chosen significance level, we would reject the null hypothesis. This would suggest that there is enough evidence to say that the residuals are not normally distributed. But if the p-value is greater than the significance level, like in this case, we would fail to reject the null hypothesis. And this would suggest that there is not enough evidence to conclude that the residuals depart significantly from normality. So the p-value here, in our case, it's really high, it's 0.7. It's not less than 0.05. So there is no strong evidence to reject the null hypothesis. We don't reject the null hypothesis, so the residuals, we may assume basically the residuals are approximately normally distributed. So let's write this down. P-value is greater than 0.05, which is the significance level, right? Indicating that there is no strong evidence to reject the null hypothesis. Thus, look, we conducted 2 tests and both of them confirmed that we have normality in the residuals. We might assume that the residuals are approximately normally distributed, and approximately. So to conclude that we don't have major violation of the assumptions. We have only one kind of violation, but in general, the general theme that we have a good, or most of the assumptions are met. So we may rely on the regression model that we have built. Okay, so this might be the conclusion of this scenario and this case, that yes, we may rely on the linear model that we built. So for the level of this class, we'll not discuss how to conduct some remedies for the heteroskedasticity issue. But in summary, the heteroskedasticity here doesn't necessarily invalidate the entire model, and it does raise a concern about the precision and the reliability of the estimates. But in general, we are good. We're gonna rely basically on the model that we have built in this level of this class. So this is the summary of the whole chapter. We did 3 things. We built a model, then we selected among models, we picked the best one, then we conducted the assumptions check, and we concluded with that the model was okay and we can rely on this model. Thank you.